Good evening, everyone. Welcome to the Aquarium. I'm Jerry Subel, president of the Aquarium. It's great to see all of you who are here this evening in the theater, and I also want to welcome all of you who are watching online. I want to acknowledge our sponsors, Gazette Newspapers and the Downtown Marriott Courtyard, for making this lecture series possible. I would ask those of you who are in the theater to silence your cell phones and refrain from texting for the next hour. I'm very pleased to welcome Dr. Ann Cohen, who is going to discuss the science behind her mission to uncover the world's most resilient coral reefs. She's an associate scientist at the Woods Hole Oceanographic Institution, and research in her laboratory at Woods Hole focuses on climate change and the impact on life in the ocean. She's the author of over 80 scientific peer-reviewed journal papers. She has served as an expert witness to the United States House of Representatives, the Science Steering Committee for the International Intergovernmental Panel on Climate Change, that's the IPCC, and the Center for Ocean Solutions Working Group on Corals and Climate Change. She's currently a member of the Ecosystem Management Working Group of the National Oceanic and Atmospheric Administration Science Advisory Board. Her work has been featured in National Geographic, the Discovery Channel, US and Canada, Public Radio International's The World, the BBC, and WGBH Nova. She's one of the founding principals of Super Reefs. It's a partnership of scientists, non-governmental organizations, and governments of coral reef nations to identify and protect climate-resilient coral reefs. She grew up in South Africa and did her undergraduate and graduate work at the University of Cape Town. We've had a very stimulating afternoon with Ann. We're hoping to do a Science on a Sphere experience with her on Super Reefs. Please join me in welcoming Ann Cohen.
So I want to open this talk today with this beautiful shot that we took during an expedition to the Phoenix Islands, which is in the Central Pacific, just a few months ago. And what I want to show you is how a coral reef is built to attract lots of different kinds of organisms, big and small. And what I'm going to do in the next shot is zoom in on this coral here. This is a Pasillipora, to show you that the coral is actually made of living creatures. These are called coral polyps. And when you peel, all the different kinds of corals are all made of animals, these little sea anemone-like creatures that we call coral polyps. And this guy here is a type called a Porides. And you can see the little polyps with all their tentacles, and as the wave comes by, they're going to retract into their skeletons. I'm going to peel away that tissue, and what you see underneath is what the coral is building itself to live in. This is the skeleton, and each one of those rings houses an individual polyp. And as you zoom in closer on the skeleton, what you see is that it's built of calcium carbonate crystals. And they're not just any old haphazard crystals. They are organized in a way to create a perfect skeleton that can withstand the strength of the waves and storms. And thousands and millions and trillions and gazillions of those crystals accumulated together over thousands of years is what builds a coral reef. Coral reef that is a home to a quarter of all the species in the ocean. 9 million species so far, and still counting. Now, this is a scene from the Great Barrier Reef, which all of you have heard about, read about, seen on TV. But did you know that the US owns over 4 million acres of coral reef? And that's not just in Florida or in the US Virgin Islands or in Hawaii, but also in the Central Pacific. We own and manage some of the most pristine, productive, glorious coral reefs on the planet. And those coral reefs, even though they take up less than 1% of the surface area of the ocean, they're working very hard, and they work for us. Here are some statistics that maybe you didn't know about coral reef ecosystems. This image here on the left shows an island of Tahiti. And you see here the reef right here. This is a barrier reef. And right in there is a beautiful, calm harbor where folks are mooring their yachts. And you see what the coral reef is doing for those people is absorbing all the energy from the waves. 97% of the energy of the waves is absorbed by that coral reef so that this harbor is created where folks can moor their yachts, where hotels can be built on the shoreline, where children can play in the sand. That all happens because the coral reef is there. Around the world, 500 million people depend on coral reefs for food, for livelihoods, through tourism and other work. And it is estimated today that coral reefs are worth about $375 billion each year to the global economy. So these are not just gorgeous vacation places. These are working ecosystems, and they work for us. Now, coral reefs exist because the coral animal, that little polyp, builds calcium carbonate skeletons that grow and accumulate over thousands of years to build a reef. And coral polyps are very similar to sea anemones. They look like sea anemones. In fact, they're related to sea anemones. But there's a key difference, and that is that the coral polyp actually builds a skeleton, whereas a sea anemone doesn't. But the corals don't do this building alone. In fact, corals don't live alone, not the ones that that build our reefs today. This is a close-up of a coral polyp. Here's one right here. You can see the tentacles. Here's another one living right next door. And inside the coral tissue, inside the cells, are millions and millions of single-celled algae that we call zooxanthellae. And what those algae are doing inside the coral is what all plants on land and in the ocean do. They photosynthesize. They use the sunlight, and they use nutrients from the ocean, and some nutrients actually come from the corals. In fact, corals pee. And the symbionts use that pee to make amino acids. And they fix carbon. And they provide that carbon and those amino acids to their coral host, the polyp. So the coral gives the algae a place to live, and the algae, in turn, provide the coral with food. In fact, about 75% of the daily metabolic needs, energetic needs of the coral, come from these little algae that live inside its cells. And it's because of this close association between the coral animal and its symbionts that we get coral reefs. Now, all the corals that you know, that you see on coral reefs, that build the reefs, have housed these symbionts in their tissues. And I don't know how familiar you are with the reproductive habits of corals, but corals have babies, and some of them actually get pregnant, and they grow the little larvae inside their stomachs, and then when the full moon comes out, the babies get ejected out of the mouth of the mother, and they go swimming off to find a home. And I wanted to show you Excuse the music, this is my students having fun. This is a baby coral. It's 24 hours old. It's called a planular larva, and it's about 70% fat. And it got all the fat from its mother. Mother sent it off into the world with a blob of fat that it could live off for a while. And what that baby is doing is it's sniffing down on the surface of the coral reef, looking for a place to live, because it's very important where it chooses to stay, because it could be there for the next 500 to 800 years. Really important. But notice the baby is green. And the reason it's green is because it didn't only get the fat from its mom, it also got those algae that are going to help it to grow into a big colony. Now, after about 3 days, that worm-like planular larva will metamorphose into what we call a primary polyp, the first polyp coral animal of its generation. And you can see here, it's got a central mouth, it's got tentacles, and it's very, very green because it's loaded with symbionts. It's loaded with those little algae. And after about 3 days, underneath this primary polyp is a beautifully formed skeleton. And you can just imagine the first coral reef that ever grew on Earth. It grew because a tiny planular larva settled there, metamorphosed, and started to build a skeleton. And all the corals that you ever see on the reef, no matter what that baby coral turns into, if it's a huge branching acropora, or if it's a Platypachyceros, or if it's a brain coral, or if it's a Montastra cavernosa, which you find a lot of in Bermuda, all of those corals that are building the reef are living in an intricate association with symbiotic algae. And sometimes that intricate association goes wrong. When the water gets too hot, and it actually doesn't have to be that hot, just about 1 degree Celsius above what corals are normally used to, the algae start to produce toxins. And the environment inside the coral becomes kind of nasty. And the coral spits out the algae. And because the algae give the coral its color, the coral looks white. And so we say it's bleached, because it looks like it's been bleached. So this is a photograph of a coral colony that we had been tracking through a bleaching event in Taiwan. And just a few days later, the coral died, all the polyps in the coral died, and the skeleton became covered in algae. And the problem is that the oceans are warming. So the reefs that we know today, the coral reefs on Bermuda, in Florida, in the Caribbean, those ones in the Central Pacific, they've evolved over a period of about 10,000 years. Those reefs are about 10,000 years old. And they evolved in water temperatures that are cooler than they are now. So the relationship between the symbionts and their host, the coral polyps, also evolved under water temperatures that were cooler than they are today. This plot is probably very familiar to you. This is the ocean heat content over the past 50, 60 years. The black line here, you can see how the ocean is heating up as the carbon dioxide concentration of the atmosphere is increasing. So the oceans now are warming more and faster than the coral reefs out there today had ever seen before. And what we're witnessing are mass bleaching events. So in 2015, so just under 3 years ago, almost 3 years ago, a massive El Nino developed in the Pacific. It was so big, it's the kind of El Nino that we call super El Nino. And this plot that you're seeing here with some of the coral reefs that we study identified is a sea surface temperature anomaly map. So what it's showing you is how much warmer the water was in the Pacific Ocean in 2015 than it normally is. And the scale here gives you an idea of how much warmer it was in degrees Celsius. So around the Great Barrier Reef, it was between 1 and 2 degrees warmer. In the Central Pacific, it was 3 up to 4 degrees warmer during this El Nino. And in 2015, we knew a lot about coral reef bleaching because at this point, we've lost about 20% of the world's coral reefs because of temperature-induced bleaching. And all eyes were on the Great Barrier Reef at that point. Everybody was watching to see what was going to happen to the iconic Great Barrier Reef during the Super El Nino. And as you may have heard, the outcome was not pretty. Across the whole northern Great Barrier Reef, up to 93% of the corals died. Absolutely devastating loss. This is something that the northern Great Barrier Reef has never, ever seen before. And the corals responded. Many of them like this. This is a scene from a scientific expedition in 2016. And at that time, we were actually watching this area here. So while the world was focused there, we were looking right there, in the middle, in the bullseye of the El Nino, where some of the most pristine and productive coral reefs exist. And you can see that the temperatures in that region were a lot higher than they were in the Great Barrier Reef at the same time. And the reason that we were so interested in this area is because these coral reefs have a history of heat waves. They've seen heat waves every 3 to 7 years for centuries, probably for millennia. So in this plot, what I've done is shown you levels of heat stress. So when we talk about coral bleaching, we don't just talk about temperature, we talk about heat stress. And heat stress combines the size of the heat anomaly as well as its duration. Because the longer it's hot for corals, the worse it is, the more the heat stress. And these data go back to 1980, which is the start of the satellite era. The satellite era is the time period over which we can calculate the sea surface temperatures really well. So this is the thermal stress history, or the temperature stress history of the Central Pacific, and this is the temperature stress history of the Northern Great Barrier Reef. And this is 2015. This is the thermal stress in 2015 that caused 93% of corals on the Great Barrier Reef, in sections of the Northern Great Barrier Reef, to lose their lives. And what you see is that in the Central Pacific, in that bullseye of the El Nino, the heat stress episodes are massive and frequent. And what you're looking at is the yellow is where we expect bleaching to happen, and the red is where we expect death from bleaching due to the thermal stress. All right, so we're talking about the bullseye of the El Nino, where it gets really, really, really hot. It's also really far away from anything. So it's not like scientists have been out there over this time period, watching to see how these coral reefs respond to these El Nino heat waves. So we got on a ship. Well, not quite a ship, a sailboat. We have a fabulous relationship with an outfit called Pangaea Exploration, which owns a 72-foot sailboat. And we were able to charter that boat. Actually, we've done this multiple times now, from Hawaii into the deep central tropical Pacific. And what are we looking for? Well, we know that these coral reefs have seen massive heat waves, multiple heat waves over long periods of time. But we don't know how they respond. How can we know? Who can tell us? How can we go back in time? These guys. These massive corals, these are the elders of the reef. They've been there for hundreds of years. In fact, the oldest coral that we've worked on is 800 years old. They've been sitting on the reef, and they can see what's been going on during when those heat waves come through. And they record that information in their skeletons as they grow. So we go out there, and one of the things we do is we take a drill, a handheld drill, and we take a biopsy into the coral. And this is what it looks like. We call it a skeletal core. It's actually like a biopsy. And all the information that we'll ever need to know what has been happening on these reefs as these heat waves come through is contained in this skeletal core, this biopsy. So what do you see when you look at that? Nothing. It's white. That's it. So to uncover this information, what we do is we ship all our cores back to Woods Hole Oceanographic Institution, where we have a CAT scanner. And we send our coral cores through the CAT scanner. We have to enter the patient name, and we have to enter the position of the patient on the bed, et cetera, et cetera. Before we had a CAT scanner at Hui, I actually used to go to the hospital and sit in the line with all the broken legs and arms, holding my coral cores, waiting for my turn. Let me show you what we see inside. So here's the core, and here's the CAT scan. Now there's two bits of information that we're immediately interested in. The one, and I'm not sure if you can see it very well on this, but there are bands here. Can you see them? Those are growth bands. Those are bands like rings on a tree. And they help us to age the coral and to know where we are in time. So this coral was collected in 2014, and we can go back, and this is the 2005 band. And this bright white band here is what we're after. This bright white band is a stress band, and it's deposited when the coral bleaches. And what we find is that the more corals that have stress bands, the more the reef has bleached. So we can make a direct correlation. How do these stress bands form? Here's a healthy coral. Here's a bleached coral. Here's a core out of the healthy coral, and this brown stuff here is the tissue, the coral polyps that I was showing you earlier, inside the skeleton right there. And you see how the healthy coral is really fat, the tissue layer is really wide, and in the bleached coral, because the coral is starving, it's actually starting to eat its own flesh, and it's becoming thinner and thinner and thinner. And we find that the stress band, this high-density white band, forms in the corals that are bleached and are starving. So we know that when we take the biopsy out of the coral and we CAT scan it and we see this bright white stress band, that was laid down there when the coral was bleached and starving. Now, in the Central Pacific, what we see in our long cores is a long history of bleaching. So there's a stress band here in 98, there's one in 87, there's one in 65, 1948, 1942, 1915, 1888. And these stress bands come in, these bleaching bands come in during the heat waves, during the El Niños. So what we're seeing are reefs in the Central Pacific that are frequently and intensely exposed to heat waves. And we see evidence of bleaching on these reefs. The question is, how severe is this bleaching? So because we have this information, what we can start to do is combine the severity of bleaching with the temperature information that we have from satellites and other data. I have trouble with this. And we can start to create, from all the different reefs that we study, measures of thermal stress or measures of thermal resilience, thermal thresholds. So on the x-axis here is the heat stress that's required to induce X amount of bleaching on the reef. And this is the information that we get from these skeletal cores. These are the data for the Great Barrier Reef, the northern Great Barrier Reef. So what you see here is in order to induce 60% bleaching in the northern Great Barrier Reef corals, you need about 4 units of heat stress. Okay. Let's see what Palau looks like. For Palau, to get the same amount of bleaching, you need about 8 to 10 units of heat stress. So Palau is even more thermally tolerant than the northern Great Barrier Reef. And here we're starting to get into the Central Pacific. In the Gilbert Islands, you need more heat stress to cause the same amount of bleaching in the Gilbert Islands than you do in the Great Barrier Reef. Phoenix Islands. Phoenix Islands Marine Protected Area. Wow. You need 5 times more heat stress in the Phoenix Islands to get the same amount of bleaching than you do on the northern Great Barrier Reef. And to the west of the Phoenix Islands, there's Jarvis Island. Whoa, we're getting like tons more heat required to induce the same amount of bleaching. So what we're learning from our cores, from these giant corals that have been sitting on the reef for hundreds of years, that are seeing what's going on and recording it in their skeletons, we're learning that the coral reefs in the Central Pacific have much higher heat tolerance than the corals in the northern Great Barrier Reef and even the corals on the barrier reefs in Palau. And we're still investigating the mechanisms or the machinery for how this happens, how these corals are so thermally tolerant. But it's likely due to the fact that they see heat waves every 3 to 7 years, and they have done for hundreds, if not thousands of years. They've figured out how to deal with the heat. But there's an even more important aspect to the story that I need to share with you. Because the ocean heat is just charging along. It's charging along upward. There seems to be no stopping it. So what happens to these reefs when we exceed the thermal threshold, when we exceed the thermal thresholds of even these most resilient, resistant reefs? Well, we have an example of how the Central Pacific works from huge Central Pacific El Nino that happened in 2002, the year my daughter was born. This is a scene from the Phoenix Islands just after the 2002 El Nino devastated the marine protected area. 75% of the corals were lost. These corals, these magnificent tabletop corals in Canton Lagoon, were all dead. But by 2009, when expeditions started going out there, what we noticed was that the corals were coming back. So these are the old dead corals, and these are the new baby corals starting to grow on top of the old dead corals. And I'm going to show you later that these fish play a very important role in that recovery. So 2002 El Nino, which was this one here, devastated the reefs in the Phoenix Islands. They came back almost to what they were before by the time the 2015 El Nino hit. Now, what I want you to notice, what you can obviously see, is that the amount of thermal stress in 2002 was actually less than what was happening in 2015. So even though we have these very thermally tolerant corals in the Central Pacific, the question is, what happened in 2015? Nothing. Very little. So here's the same scene in 2002 and 2015. Those baby corals that recolonized the reef after the 2002 event grew up, became adults, and were much more thermally tolerant than the ones that occupied the reef in 2002. So we think what we're seeing is we're starting with very, very thermally tolerant corals, and then even when they hit their thermal threshold, the maximum that they can stand, and they do die back, they're able to come back. And they come back each time stronger. We're almost seeing an evolution in action in the central tropical Pacific. I wanted to show you another example, a very, very similar one, that we're seeing play out right now in Jarvis Island, also in the central tropical Pacific, but this is actually a US managed area. Jarvis Island is probably one of the most productive reefs on the planet. In fact, in 2012, it was rated the healthiest ecosystem on the planet under the Ocean Health Index assessment. This is a scene from Jarvis Island just prior to the El Nino in 2015. When we got out there in November 2015, the coral reefs had been under severe heat stress for about 7 months. And what do you see? All the corals, everywhere you could see is bleached. The corals were still alive, about 80% of them were still alive, but they were bleached. They'd lost their symbionts. They'd ejected their symbionts. And when we went back there in May 2016, 95% of the corals were dead. In 2015, Jarvis Island exceeded its heat threshold. It was seeing heat that it had never seen before, and this is what happened. When we returned in May 2016, the surface of the reef was covered in turf algae and cyanobacteria. There were very few live corals. Most of the fish had disappeared. It was a graveyard. These guys are really, really important. What they're doing, they're also really cute. They're feeding off of the turf algae on the surface of the reef. They're the reef cleaners. Their role in reef recovery is massive. If it wasn't for them, the coral and algae wouldn't be able to settle. The fish, the grazing fish, keep the reef clean. They enable the coral and algae to settle. The coral and algae is a cue for settlement of new baby corals. So what we're seeing on Jarvis is that whole trajectory play out. By the time we were there in 2017, new baby corals started to colonize the reef. We're also seeing corals come back from the dead on Jarvis Island. This coral, number 1497, seriously, this is our coral ID, 1497, died. Well, it looked like it was dead. There was no sign of living tissue when we got there in 2016. By April 2017, it had almost fully rejuvenated. So once again, what we're seeing is an ecosystem, and luckily an intact ecosystem, which I think is very important in the recovery of these coral reef systems. An ecosystem that has figured out how to come back, how to revive, how to recover from catastrophic mortality caused by bleaching. So we found this incredible system in the Central Pacific, incredible systems in the Central Pacific, which, because they've been exposed to natural heat waves with El Nino every 3 to 7 years for so long, they've kind of figured out a way to deal with this heat stress. One way is to elevate their thermal thresholds, so they're very strong to begin with. Then, as their thermal thresholds are exceeded, they're able to recover. We're very interested to figure out how this all happens, so that science of that machinery is still underway. These are reefs that we call super reefs, and the reason we call them super reefs is because they have figured out how to deal with heat. So they probably, most likely, have the best chance of surviving future warming. As that warming graph just keeps on going, these reefs have a chance to adapt to that escalation of heat to a certain point. If that warming trend just keeps on going, there's going to be a point, most likely, where no coral reefs can survive. So our goal now, in this narrow window of time that we have, is to go out into the world and find where all the super reefs are. And then we work with the governments of those countries to ensure that those reefs are protected from the other things that can kill them, like dynamiting or dredging or pollution. All of these things are still going on out there on coral reefs, although it is a lot better than it was 30 years ago. But there is still dredging, there is still dynamiting, there is still poisoning of reefs. What we want to do is go out and find all these super strong coral reefs and make sure that the countries know that they have these reefs and then protect them. And we found reefs outside of that central equatorial Pacific region. Just to the north of the Phoenix Islands, Howland Island came out of the 2015 El Nino relatively unscathed, even though it too had seen, in 2015, the highest level of heat stress it's ever seen. So this reef saw the same level of heat as this reef, but the outcome was completely different. We're also finding reefs in the northern South China Sea, some around Taiwan, some further south, which are also able to live through these heat waves, come out unscathed. One of my favorite places on the earth, Palau Rock Islands have some of the most heat-tolerant and pH-tolerant corals that we've ever studied. Unfortunately, this area here, called Nico Bay, one of the most beautiful areas I've ever seen, is not currently under protection. So we are trying very hard to work with Palauan government to ensure that it prioritizes this region so that the supercorals in there are not destroyed. Southern Line Islands is another set of reefs that came through the 2015 El Nino unscathed. And we're currently working with the government of Kiribati to launch an expedition there next year to study these super reefs and also to work into the marine protected area the protections for these corals. So I hope that what I have talked with you about today, are some things that you didn't know about corals, and B, that even though corals face increasingly devastating and challenging odds, there is still hope out there. And there are still things that we can do to ensure coral reef futures. The yellows, or the black dots there are all the coral reefs in the world, the tropical coral reefs, the ones that occupy the shallow water. And the yellow stars are where so far we have uncovered super reefs, reefs that are remarkably tolerant to ocean warming. And we know that there are more. We've actually started to use the information that we're getting from these reefs to predict where other super reefs might be. And this is just the start of our places to look. These are where the models are telling us that we have high likelihood of finding reefs that can tolerate extreme heat. Our next target, our very next target, is a country called Tuvalu. How many of you have heard about Tuvalu? It's just to the southwest of the Phoenix Islands in the Central Pacific. It's a country of 9 coral reef islands and about 10,000 people. And I had the most extraordinary opportunity just a couple of months ago to visit Tuvalu for a climate change Sautalaga. And I participated in the dancing, although I didn't get a picture of myself. But I had the most fabulous time amongst these absolutely fabulous people, so much laughing and dancing and singing. I actually did not want to come home. But I did escape some of the meeting to go and check out the reefs on Funafuti. And what I found was that this area here, a lot of the corals were dead from the 2015 El Nino. But I had the wonderful opportunity to snorkel all across this area here. We're talking about several kilometers. It was just so glorious, I just couldn't get out of the water. And the corals there were absolutely glorious, thriving and healthy. And even though they'd just seen a massive heat wave come through, they had somehow figured out how to deal with it. I have some ideas about how they're doing this. And I'm hoping to launch an expedition next year to conduct the science that we need to determine that. I'm having trouble with this clicker a little bit. There we go. So in this huge scientific endeavor, and sometimes I feel like I'm taking on the world, I have fabulous partners, and I'm making fabulous new friends and meeting wonderful people, all of whom are as invested as I am in the future of coral reef ecosystems. But I just wanted to introduce you to some of my graduate students, Nathaniel Malika, Tom DeCarlo, and Hannah Barkley. And they were really with me at the beginning of the Super Reefs endeavor. To figure out the toolkit that we could use to uncover the magic of super reefs. And some of our funding partners are also listed there. And that's all that I have for you today. I actually have tons more I could say, but I thought maybe I should end it and just say thank you so much for your attention.
You're a great, great speaker.
Thank
All right,
you.
bring the house lights up. Who has the first question? Okay, Linda's got a microphone over there. We saw you last night.
Thank you. I have two questions, actually. What's the average depth of the coral in the ocean?
There's corals and corals.
Like one?
There's lots of different kinds of corals. So the corals that I'm talking about here, the super reefs that we're discovering, those are shallow water, warm water corals. And you can find them to about 100 feet depth, 100-foot depth. But there are corals that live like 2 kilometers down in the ocean, the deep water corals. And I don't go that deep.
Well, is there a temperature gradient from the bottom to the top?
Yes.
And what is the average temperature gradient? I mean, how does the temperature gradient go the lowest to the highest?
It really depends on where you are. But some places it can be 1 or 2 degrees. And in some areas that we work, we are exposed to what we call internal waves. And this is where water from really deep comes up onto the reef in these internal waves. And it's freezing. We're diving there, and it's so nice and warm, and it's so glorious. And then suddenly, oh, you feel like you're in the North Pole. Those are just, but generally, the temperature gradient is max a couple of degrees.
Linda, you've got another one right over there.
You mentioned pH at the end there a little bit. Is acidification a bigger problem? Are reefs reacting to that in the same way or differently?
That's a really, really good question. So I'm not sure how many of you are familiar with ocean acidification, but that's also a product of carbon dioxide emissions. The oceans are absorbing about 26% of the carbon dioxide that's going into the atmosphere, and that's causing the pH of the ocean to drop. And because coral reefs are built of calcium carbonate crystals, you know what happens when you drop a calcium carbonate crystal into acid? It dissolves. And that's actually very similar to the concerns that we have for coral reefs. But we put that in perspective. The ocean acidification problem is a long, slow, sublethal issue. It's not clear to us yet whether coral reefs will actually die from ocean acidification. Whereas a heat wave can come through, and in less than 2 weeks, the whole reef is dead. That's what we're mainly concerned about right now. Ocean acidification is certainly an issue, and I think, to be honest, in the recovery of reefs, because reef recovery from heat waves is so dependent on the baby corals growing really fast, that's probably where ocean acidification is going to have the biggest impact in recovery. But right now, the reef pH for most of the coral reefs, they're not at a point where they're starting to dissolve yet. But they are dying from heat.
Where do you suppose the baby corals are coming from if there is mortality in the reef? Were those corals that died, putting that in quotes, perhaps dormant or hibernating or something like that?
That's a really, really good question. And we're like racking our brains. We're trying to figure that out. And one of the ways we're going to do that is with genetics. But in these catastrophic mortality events, there are always some corals that live. So even on the northern Great Barrier Reef, where you see these huge, kilometers of reef that are dead, there are some corals there that somehow manage to make it through. And that's the same for the Central Pacific, for Jarvis Island, where I showed you the pictures of the little babies coming back. About 5% of the corals survived. And I think that's the trick. Because the ones that survived are obviously the heat-tolerant ones. They're making heat-tolerant babies. Those heat-tolerant babies are seeding the reef. And then the next heat wave comes through. They have more heat-tolerant than the previous reef community did. They still have a threshold. Presumably, they might hit that threshold at some point. But I think what nature is doing in these places is weeding out the thermally sensitive ones, and then we're kind of becoming more incrementally more thermally tolerant. I mean, that's an hypothesis that we need to test.
You know, first of all, thank you for a great lecture. This can be kind of a tough house sometimes on lecturers. Just ask Jerry when he tries to give a lecture. But I have a question. The Great Barrier Reef, of course, is stressed by other environmental questions, the nitrogen fertilizer runoffs from being too close to civilization. And these islands sit out in more pristine areas where they don't have that weighting on them. And so the people that live out there should value that just for tourist money. You know, that's your big economic gain out there. But so they obviously don't have that human contact pollution out there to the degree that
Not
the Great
to the
Barrier
same
Reef
extent.
has.
Although the northern Great Barrier Reef is probably one of the, or was probably one of the best managed and pollution-free areas of the Great Barrier Reef, and yet it still suffered that devastation. I think a lot of that had to do with the fact that it's just never seen that level of heat before. But you are right. That picture of the footage that I absolutely love of those fish all eating the... Yeah. And you see, as the videographer is getting closer, they kind of all move away, but they're still eating. They're so intent. And they're all in line. They're moving away. They're so cute. They play a huge role in the recovery. They're the natural reef cleaners. They come in and they make the surface, wipe the surface clean so that we can start again.
Have another one here.
And with overfishing, that's a huge problem because the fish are, yes.
Fish have to be protected.
And that's what's happened in the Caribbean. Yeah, exactly. It makes so much sense, doesn't it?
Too logical for politicians.
Is it safe to say that the evolution of the coral, considering that there's been these heat events for centuries and perhaps longer, that it's not something new, that it's something that is just, it's evolution over centuries or millennia? Because the El Nino is something we just discovered recently, but it's likely to have been happening longer, or other heat events might have been happening longer.
Well, El Nino has been around for a very long time. Yes, it's a natural part of the climate system. It is becoming more intense under global warming. So the last 3 super El Ninos were all within the last 30 years. But yes, you're absolutely spot on with what I'm thinking. And that these reefs actually didn't always start off with that the thermal thresholds that they have now. It's developed over time. And the particular oceanography in that region allows that to happen. It's an hypothesis. As a scientist, I don't ever want to say something's true or not true. It's all sort of, you know, we're working towards testing whether that is actually what's going on. And if it is, it's absolutely remarkable. Well, I think what we're seeing out there is absolutely remarkable. I mean, you saw those side-by-side images of the Great Barrier Reef and Howland Island. They saw exactly the same level of thermal stress in 2015, and yet Howland Island just looks so different.
Can I ask a follow-up?
Yes, yes.
Are some types of coral more tolerant than others? Because we know there's different varieties of
Yeah.
Some are more tolerant to higher levels of heat. And when you talk about the heat stress, that index, what makes up the index? Because you talk about a number, but is that just simply the ocean temperature, or are there other factors or criteria involved?
So the index is a combination of how much hotter the temperature was above what the corals normally see in the summertime, so their hottest average, combined with the number of weeks that it's above that temperature. It's actually, NOAA actually developed the stress index. It's called the degree heating weeks index.
So we have one there and then one.
Yeah, most of these are all located in a central band across the oceans, equatorial, if you will. It's hot there anyway. Do you have any information as far as salinity affecting anything? Because you have increased evaporation, makes the water saltier, et cetera, et cetera, et cetera. Does that have any effect, or is that a cumulative thing that, occurs because of evaporation and the increased heat in the ocean?
That's a really good question. On the reefs that we've studied so far, and the super reefs that we've discovered so far, the salinities are not outside of the normal range of salinities that you'd find across the tropical ocean. There is actually a natural gradient in salinity from the west to the east. We don't see a correlation between salinity and superness.
So they'll grow in a, extremely saline environment just as easily as
Oh, I see what you're asking.
highly
I don't actually
oxygenated
know
and
that.
et cetera? Are they?
We have not had the opportunity to test that out.
Okay. Fair enough.
But the reefs that we study are not outside of the normal range of ocean salinity for the tropical regions.
Yeah, I was just thinking because they're not very deep in the water column, that they'd be affected by surface changes, whereas down lower where there's less heat, that would change and the salinity level would be more evenly distributed there. Just a thought.
That's actually a really good point. When in the Central Pacific, we were talking about the gradient of heat from the surface to like 100-foot depth. During El Nino, that gradient just goes away. The whole thing down to 100 foot is like a bath. It's a hot tub.
Chris, oh, you got it.
All that gradient just becomes completely homogeneous.
Okay. I realize you haven't done research on Tuvalu yet, but I was fascinated with your image. And I wondered if you have like impressionistic hypotheses. Did you experience more cold water upwelling on that northern part? Or I wondered about currents. Does the amount of, transfer of water in currents make a difference?
That is, you can come and work with me. Okay, so you remember that map that I showed? And the red area, there's channels in the reef there where cool oceanic water is always flowing through. So the corals on the west side are usually bathed in water that's actually quite cool, whereas the corals on the north are always in hot water because there's no cool ocean water coming in.
So that goes back
So there, I think it's the opposite. So when the El Nino came in and heated everything up, the corals on the west side are used to being cool. So they were like, what the hell's going on?
Yeah.
I can't deal with this. And they died. But the corals all along the north were like, another sunny day.
Interesting. Thank you.
That's my scientific hypothesis.
We're going to take one more.
How does the rise in ocean water or these El Ninos affect the fish life, the reef cleaners, because as things, has there been studies about, how those are affected? At what point do the reef cleaners die off and then the coral are in real trouble?
That's a really good question, and I actually don't have the answer. My sense is that fish are a lot less sensitive to relatively small, like 1 degree, 2 degree changes in heat, and also to pH, changes in pH, than the corals, although maybe you disagree. So, and they can move. And what we see when we go out there in the peak of El Nino is that an area that's once got tons and tons of fish, the fish have sort of like all gone. And we think that they haven't gone somewhere else, they've just gone deeper. They've kind of gone into hiding much, much deeper. And then when the ocean conditions return, they come up and they clean out the reef.
You know, remember that old saying, if stress, if it doesn't kill you, it makes you stronger. And I think there's a wonderful book that was published recently called The Coddling of the American Mind. And the argument is that we're doing our children a terrible disservice by trying to protect them from all the stresses in life. And one can argue about that. But it was a great lecture, and I want to thank Ann. And we're now involved, as Ann mentioned. We have a seat on the board of the Phoenix Island protected area. Anthony Brown, our CFO, occupies that seat. And we're looking forward to working with Ann and all her colleagues in the Phoenix Islands. So, Ann, thank you very much for a great, great talk.
Thank you. Thanks. Great questions, too. Yeah. Thanks for your wonderful questions.